Hello. So today we are talking about electronic configurations of lanthanides and their ions. Students often get confused when a single lanthanide atomic number is given and asked to write the electronic configuration. So by looking at this video, you can overcome it, and by looking at this video, you can solve the question within 1 minute or less than 1 minute. How exactly they look like? So these are the lanthanides you can see here. So there are 14 elements after lanthanum. So they are cerium 2, lutetium. There are 14 electrons, 14 elements are there. So 14 elements have different electronic configurations, and their ions also have got different electron configurations. So lanthanum has +2 configuration, lanthanum +3, lanthanum +4 configurations. Recently, the same question asked in the NEET, which of the following has got 4 unpaired electrons in the f orbital? So most of the students have gone wrong because they have to work out entire lanthanide configuration. Otherwise, they should know this trick to solve it. So best method to solve this trick is the way I solve the question, right? So let's get started with this. So here, so lanthanides electronic configurations. Let us start it. So these are the lanthanides. So how exactly lanthanides and their electron configurations have to be studied. So these are the lanthanides, and the general electron configurations of lanthanides is, of course we know that electrons in lanthanides fill in penultimate shell. The electrons in the lanthanides fill in n-2 f orbital, and there would be 1 to 14 electrons will be filling in n-2 f orbital. So n-2 f orbital has 1 to 14 electrons. n-1d has got 0 or 1 electron configuration, and ns2 have got 2 electrons. So in nth orbit, 2 electrons fill up. In n-1d, only few elements, in fact only 3 elements have this 0 1 configuration, and remaining 11 elements have got 0 configuration, and n-2 f 1 to 14. The problem comes where, what is 1 to 14? So that's how we have to figure it out. So how many electrons are present in the f orbital is our motto of the video today. So f to the power, I wrote it x, so this is what we have to figure it out. So for this I have a simple formula by which you can write in 1 second. 1 or 2 seconds you can just write, just you need to do a simple subtraction by which you can solve it. So the question comes up, the formula is this one, f to the power x equals to atomic number of lanthanide minus 54 plus 2. It should be, wait a minute, it's not like this, it should be, wait a minute, 54 plus 2, 54 plus 3. Yeah. So the formula to calculate f electrons in lanthanides or in actinides, so is this. For lanthanides we are looking to that 4fx equals to atomic number of lanthanide, you subtract these two numbers. What are these two numbers exactly? 54 is the nearest noble gas configuration. That's what we have to subtract from its atomic number. And we have ns2 electrons also. So these 2 electrons needs to be removed from this, so that we left with all f electrons. So atomic number of lanthanide minus nearest noble gas, that is xenon 54, plus subtract and the 2 more electrons from the s orbital, that will leave you with f electrons. But there are 3 exceptions for it. 3 exceptions are what you know. The first one is the first element. For first element, you need to subtract 3. Why? Because in lanthanides, first element, 7th element, and the last element have got D1 configurations. So first element, central element of the lanthanide, that is the seventh element, gadolinium, and the last element have D1 configurations. So for these three elements, you have to subtract 3. You have to subtract 3. So that is atomic number minus 54 plus 3. So this gives you the exactly F electrons for this first element cerium, gadolinium, and the last element lutetium. Simply we'll do it. Right. So when it comes to ion, it is very easy. Most of the time ions configurations are generally asked. So for ion case, so F to the power x equals to atomic number subtract 54 and oxidation number of the ion. Just so this atomic number minus 54 plus oxidation number gives you exactly F electrons present in the lanthanide ion. Let us see few examples, then we will come to know this. So first let us start with the cerium. So we have to write cerium electronic configuration needs to be written. How exactly we do it? So this is the first element. So therefore atomic number is how much? 58 subtract nearest to noble gas of cerium is, or in fact all lanthanides is 54 plus 3. 54 plus 3. So this subtract, this will give you, so F to the power x equals to 58 minus 57, that is equals to 1. That means it has 4F1 configuration. Got it, right? Let's do the same thing for praseodymium. So praseodymium atomic number is 59. So it should be 59 minus 54 plus 2. Why I am taking 2 only? I have to subtract 3 for first element and this gadolinium seventh element. For remaining elements, just I subtract 2. So it is 59 minus 56. So 59 minus 56 gives me 3. So there means, so there will be 4F, 3 electrons are present in it. If 3 electrons are present in it. In this way, you can calculate. So in this way, you can calculate for any lanthanide ion. Let's do further continue it. Let's go for 60th element, that is neodymium. Neodymium for Nd. So it's 60 minus 54 plus 2. That's it. 54 plus 2 is 56. 60 minus 56 gives you 4 electrons. So that means it has 4F, 4 electrons are present in it. For any lanthanide, you can do it in the same way. So let's do it for 61st element. For 61st element is, so promethium. So 61 subtract 54 plus 2. 54 plus 2 is exactly 56. Just you are subtracting 56. So this gives you 61 minus 56. 4 plus 1, 5. So it has exactly 4F, 5 configuration. So when it comes to samarium 62. So samarium equals to, so it's 62 minus, again 54 plus 2, 56. Just I subtract these two numbers. So it will be 4 plus 2, 6. So it gives you 4F, 6 configuration. Right? Easier. Just you have to subtract 2 numbers. Atomic number is given in the question and the nearest noble gas is the 54. And you are also removing S electrons. So from a lanthanide, you are subtracting 54 first. Xenon electrons are removed, S electrons are removed, and we are left with only F electrons. So those electrons are given here. Let us talk about europium. Europium has 63 configuration. Europium is 63. So 63 subtract 56. When you subtract 56 from 63, so it will be 4 plus 3 equal to 7. That means it would have 4F7 configuration. Europium will have 4F7 configuration. Let us do it for The gadolinium also. Gadolinium 64. 64 is GD. So this is the very special one. Exceptional configuration. In atomic structure is also it's mentioned. You have to remember that in order to have half filled f orbital, it pushes one of its f electron into s or d orbital, so that it remains with the f7. But if you don't remember that also, you can solve here. So it should be 64 subtract 54 plus 3. So you have to subtract 57 for gadolinium. Why? Because there is one s or d electron. So this is nothing but 64 minus 57. So this also gives me 7. So that means it has 4f7 configuration. 4f7 configuration is there for this gadolinium. Easy, just you subtract it. For 58 minus 57 gives you f1. f2 is missing, you can check here. 59th element, 59 minus 56, f3. For 60th element, so 60 minus 56, 4f4. For 61st element, 61 minus 56, again f5 configuration. In the same way you can solve for other ones. So let us also see the remaining ones. So it will be easy for you to solve if you know the trick. I have to write for 65th element. So what I will do here, 65 minus 54 plus 2, 56 karunga bas. So this is going to give me 4 plus 5, 9. So it gives me f9 configuration. This gives me f9 configuration. Is it 65 minus 56 is going to be 15 minus 6. Cut here. Yeah, it gives me 59. Why? Because the d electron. So for 65 minus 56 gives you f9 configuration for terbium. It works for all the elements as well as ions. Let us go for dysprosium. Dysprosium is 66. So it is 66 minus 56, exactly 10. So it will have 4f10 configuration. Helium. Helium has 67. So it is also 67 minus 56. So exactly f equal to how much? 11 electrons are here. In the same way, erbium. So 68 minus 56. Why I am subtracting 56? 54 plus 2, 56. So this gives me exactly f12 configuration, right? 69th element, thulium, 69 minus 56, again f to the power 13. Yeah, as simple as that. And 70th element, lutetium, so 70 minus 56 gives you f to the power 14. f14 are there. But lutetium is the last element. So here you have to take care of it. That is 71 minus. So here you have to subtract 3. Why you have to subtract 3? Because the first element, last element and 7th element have D1 configuration in lanthanides, and no one else have D1 configuration at all. So therefore this also gives you F14 configuration. In this way, if one element's atomic number is given and you ask to solve it, just subtract xenon atomic number and s electrons, you will get it. You subtract xenon, s and d electrons for first element, third, 7th element and the last element, you will get the F configurations easily. Let us also see some ions configuration also. Let us see here. We will come back to here. So ions configuration, how do I do it? I will do it again here only. I will try to do it here. Let us take, let me erase it and I will do it here. Let us see the configurations of ions. Yeah, let us take any element here. For example, I'll take the samarium. So samarium, I'll go for samarium plus 2. So I have to write the electron configuration of samarium plus 2. So my formula is F to the power x equal to atomic number subtract 54 plus oxidation number for ion. For ion there is no exception. For ion adugute, if ion is asked, it is the easiest way to solve it. So samarium is 62 minus 54 plus 2. Why I am subtracting only 2? Because oxidation number. So this is nothing but 62 minus 56. So this gives me, so 4 plus 2, 8. So F 8 configuration is here. Right? So in the same way, we'll go for europium. For europium also, it is 63 minus, so we'll go for europium plus 2. Yeah, let's go for plus 3. Europium plus 3. So 63 minus 54 plus 3. It is 63 minus 57. So this gives me 4F6 configuration. For any ion, it works exactly perfect. Even with the gadolinium also it works the same. Let us go for GD plus 3. So GD has 64 electrons minus 54 plus 3, that is 57. So 3 plus 4, so this is 64 plus 54 plus 3 is 57. So 3 plus 4 is 7. So exactly it will have F7 configuration. For any element you can do it in the same way. For any ion it is best method to solve it. Let us do some ions of these also. For these elements, for ions also we'll try it. For example, we'll try dysprosium. So 66 dysprosium plus 3 configuration needs to be written. So it has to be 66 minus at 54 plus and plus 3. 57 needs to be subtracted. So this is 66 minus 57. So this is equal to 3 plus 6 is 9. So therefore we got F9 configuration. For any ion, it is going to work the same way how we do it for the elements. Exactly the same it's gonna work. Let us see for helium. Helium 67. 67 helium plus 3. Let us try this one. So it is 67 minus 54 plus 3. So this is going to be 67 minus 57 equals to F to the power 10. Exactly the 10. For any element ion you can do it properly. In fact, it works with 3D series elements also, where you have to subtract argon atomic number and oxidation number. So that's not the topic today. So we'll see the thulium. So we have Tm plus 4. So let's do it. So it is 69 minus 54 plus 4. So this is 69 minus 58. Right? So exactly it's gonna be 2 plus 1 is going to be F. How much would it be? 58. 69 minus 58. So 11. Exactly the 11. So in this way you can solve easily by looking at this formula. For ion it is easy one. For gadolinium and remaining ones you have to remember. Let us take the question from ReNEET 2026. Yeah, this is the ReNEET 2026 question. I'll read the question here. The lanthanide ions having 4 unpaired electrons is given are cerium, neodymium, Tb, helium are given. So and their ions are given here. Right? So our formula is simple. Atomic number, our formula is simple. What is it? Atomic number minus 54. I can see all of them are plus 3. So this gives me the atomic number. Isn't it? So helium atomic number is given. How much is it? So we'll go here. Helium 67. So it should be 67 minus 67 minus, I'll do it here, 67 minus 54 plus 3. So 67 minus 57 exactly 10. So 4f 10. But the question is about unpaired electrons. So you have to distribute these 10 electrons in 7 f orbitals. There you get the answer. So 1, 2, 3, 4, 5, 6. Here is 7. Here is 8, 9, 10. So here you have 1, 2, 3, 4 unpaired electrons are here. The helium is the answer for that question. But how you solve it is important. Let us do for 58. 58 would be 58 minus 57. 58 minus 57 gives me F1 configuration. 1 will not have 4 unpaired electrons either. Right, in the same way we will go for neodymium 60. So 60 minus 57 gives me F3 configuration. So F3 will not have 4 unpaired electrons at all, it will have only 3 unpaired electrons. Tb plus 3, so it is 65 minus again 57, right? So it is going to be 4f8 configuration will be there, right? 4f8 will be there, right? 4f8 will be having how many unpaired electrons? So we have 7. So 1, 2, 3, 4, 5, 6. Here is 7 and here is 8. So unpaired electrons are 1, 2, 3, 4, 5, 6 unpaired electrons are here. In this way, you can solve it any type of question if you know the formula, right? So just let me give the formula again. Once again, I'll give you the formula for this. How exactly we do it? So for F electrons, you have to subtract atomic number minus 54 plus 2 for all 14 elements. For not for only we have 3 exceptions. So the same formula will be atomic number minus 57 for these 3 elements. First element cerium, 7th element gadolinium, 14th element lutetium. For this you have to do it. For ion it is further most and the easiest one is the ion. So it is atomic number minus 54 plus its oxidation number. Plus its oxidation number gives you F electrons. Practice this, revise the video again, watch it and practice it. You will be mastering. Thank you.